We're going to continue our study on vectors today, talking about vector operations. So first we're going to talk about scalar multiplication. Scalar multiplication is when you have a product of vector v and a scalar, or some constant, which we'll call k, and we would multiply those two, and that would give us the vector that is the absolute value of k times as long as v. Now, if k is positive, k times v has the same direction as vector v. If k is negative, k times v has the exact opposite direction as vector v. So here are some examples so you can see visually. Let's say this is vector v. If you have 1/2 times vector v, so your k here is 1/2, that means that your magnitude is going to be half the magnitude of the original vector, but it's going to have the same direction because 1/2 is positive. If you had 2 times v, then you are going to have a vector that is twice as long as the original vector v. It's positive, so it's going to be in the same direction as well. Now let's look at some examples where we have negative values. So if you had negative v, which really is -1 times the vector v, that's going to have the same magnitude, but it's going to be in the exact opposite direction. If you had -2 times v, this is going to look just like 2 times v, except that the direction will be the opposite, but the magnitude will be the same as 2 times vector v. Okay, so how do you actually apply this when you have a vector that's in its component form? So scalar multiplication rule is you take some vector, let's say vector u here, with components u1 and u2, and k is a real number. Then the scalar multiple of k times vector u is going to be this vector here. So k times u1 would be the first component, and k times u2 would be the second component. So really all you have to understand from this is that in order to multiply a vector by a scalar, you multiply both components by that scalar. All right, next we have vector addition. So visually, vector addition is where you place the vectors without changing the magnitude or direction, so that the initial point of one vector coincides with the terminal point of the other. The sum of the two vectors is what we call, let's call it a vector r, that's created by connecting the overall initial point with the overall terminal point. We call r the resultant vector. So say, for example, you have two vectors here, u and v. Right now they're not connected in any way. But if I wanted to add these two vectors together, visually what that means is I take one of those vectors and I move it until the initial point of that vector is where the terminal point of the other one is. Now it doesn't matter which one you choose to move. In either case, you should end up with the same resultant vector. So for example, let's say I keep u where it is and I move v. I move v so that the initial point is going to line up with the end point, the terminal point of vector u up here. Now notice that the magnitude of vector v hasn't changed. The direction of vector v has not changed either. We've just simply shifted the entire thing up so that its initial point was at the terminal point of the other. So the resultant vector is when we create the vector such that the overall initial point and the overall terminal point are connected, and that creates our resultant vector. So connecting from the initial point of u to the terminal point of v, that is our resultant vector r. Now, what does this look like in terms of algebraically using two components of a vector with two components of another vector, how do you actually add them together? How do you actually get the components of that resultant vector? So here's the vector addition rule. So say you had vector v with components v1, v2, and vector u with components u1, u2. Then, in order to add vector v and vector u, you would add the components v1 plus u1 to get your first component, and then v2 and u2 to get your second. Same thing with subtraction. So if you were to subtract two vectors, you would do the same thing, except subtract them instead of adding them. So v1 minus u1 and v2 minus u2. Okay, let's take a look at an example and actually apply both sets of these rules. So example 1, we have vector v equals negative 2, 5, vector w equals 3, 4. Find each of the following. Okay, so 2 times vector v, so w is not even involved in this one. So 2 times vector v means I multiply each component by 2. So I would multiply the negative 2 by 2 and the 5 by 2. So we end up with negative 4, 10. All right, let's look at the next example. We have vector w minus vector v. So we take our components for each of those vectors, the first component of w, subtract it from the first component of v, and do the same thing with the second component. So the second component of w minus the second component of v. So this is going to be 3 minus negative 2, which is 5, and then 4 minus 5, which is negative 1. All right, the last one here combines both of those rules. So we have vector v plus 2 times vector w. So writing this out, we have negative 2, 5 plus 2 times 3, 4. So I would first multiply vector w by the scalar 2. So we end up with 6, 8. And then we'll go ahead and add those components together. So negative 2 plus 6, which is 4, and 5 plus 8, which is 13. So 4, 13 is the components of the resultant vector. Okay, lastly, I just want to go over a couple of properties of vector addition and scalar multiplication with you. So these you can just write down. So the first is that vector u plus vector v is the same as vector v plus vector u. So order here does not matter. Okay, so that's really the commutative property. And the second one here is really the associative property. So if you add vectors u and v together first and then add w, it's the same as if you were to add v plus w first and then add u to that. So those are equivalent. The third one is u plus 0 equals u. So if you have what we call a 0 vector, and you add that to any vector, you get exactly what you started with. So really this is an identity property. All right. Similarly, if you were to add a vector u with its exact opposite, negative u, you would end up with the 0 vector. Okay, number 5. If you have c times d times a vector u, you can either multiply d times the vector first and then multiply c times that, or you can multiply the two scalars together first, c times d, before multiplying it by the vector u. Okay, next we have c plus d, again c plus d being scalars, and then if you multiply that by u, that's the same as if you were to multiply vector u by c, and then separately multiply vector u by d, and then add those two together. So if you look at this, this is really just some form of distribution. Okay, now what if you instead had two vectors and just one scalar? So if you were adding two vectors together and you multiplied it by a scalar, that's the same as if you were to multiply each vector by the scalar and then add them together. Again, another form of distribution. All right, now we have 1 times any vector u is going to equal the vector itself. And then if you have 0 times a vector, that's going to equal 0. And the very last property to write down, and this one looks much more complicated, so we'll try to make sure we understand it. So on the left-hand side here, we have c, so that's a scalar, times a vector v, and it's saying the magnitude of that vector. Okay, so the magnitude of c times a vector is equivalent to, if you take the absolute value of c times the magnitude of that vector. Now the reason why this works is because c is actually just a scalar, and so the scalar, if you multiply it by a vector which has components, is going to be the same if you were to multiply that vector with components first and then find the magnitude, versus if you were to find the magnitude of the vector and then multiply it by the scalar. Okay, so the magnitude of the vector c times v, vector v, is the product of the absolute value of c and the magnitude of vector v. And those are all the properties with vector addition and scalar multiplication that you should be familiar with.